I can't hear you guys.
Yes. Good.
Good now?
Yep.
Okay. Now we need to make one screen with content sharing. Okay, good enough. And we will keep John on this screen because otherwise we will not hear him. So, who we are and what are we doing right now? It is, you can slowly proceed there. We are on the group meeting of computational chemistry. If you do not think the handouts are needed, you can pass them to the next person. So there will be 5 mini talks, and this meeting is indeed unique. Why and what is going on? The computational chemistry with standard software pieces is something that anywhere with right licenses for right software can do on this planet. And typically the computational chemistry tasks, assignments are targeting the calculation of static properties of materials. So the energy levels, distribution of charges, spectra. But in many realistic situations, the properties of materials dealing with dynamics and regular, also known from standard packages, molecular dynamics does not help. So there are a lot of processes, almost any process involves dynamics of electrons. Like if you allow a system to depart from the ground state to excited, there is rearrangement of electrons in time. If it goes from excited to the ground, there is arrangement in time. And if there is a charge transfer, there is also rearrangement of the charge density in space, in time, in energy. So we are working on bringing a skill to compute this dynamics of electronic state to general public in few years and to tiny circle of group members for today. This can be implemented in many different codes, many different compiler versions, many different types of software, but right now it is implemented in the with help of Matlab software, which is simplest language of scientific computing. And before we can go to true activity, we need to overview where to get Matlab and how to install it. And they will hopefully help us in getting through this question. So if you want to point something, you may go to the screen. If you do not care, you can keep sitting. Okay.
All right, so installing Matlab is fairly easy if you are an NDSU student or if you work at NDSU. So the difference between those two we'll talk about here in a second. So first you just want to go to the home page of NDSU, go down to the I index, click the I, find information, technology services, click on that. On the left hand side you'll see software, you want to click on that. We're going to go software licensing program. and then Matlab. So now we are on the page for Matlab, and you are going to want to scroll down a little bit until you see the obtain the software portion of it. This is on the same page. You don't need to click on anything to get here. When we get down here, you're going to take one of two paths if it's your personal computer. Either you're going to contact your departmental software contact, which for chemistry is Gregory Cook. And if you're a student, you can just request the Student MathWorks account. By clicking on that, it'll bring you to the bottom of the page, and it'll just ask for your first name, last name, email address, and you can put a comment there if you want to put why you need it or whatever. So when I was doing it, I used a student personal computer because it's fairly easy. So otherwise, if you've seen as we work here, you can contact Gregory Cook and he'll email you the stuff needed to proceed. So basically, they'll send you this sheet here. It's a Word document. You just print it, sign it. You're supposed to read it. Make sure you read word for word, just like you do every other terms and conditions page. One interesting thing to note here is my signature below certifies that I will not use Matlab for missile technology. So, yeah, funny. But once you send that back, then they email you a link, and you click on the link, you log into your account with the given username and selected password, and it'll bring you to this page, which shows you your software licenses. And you can see here, the one here is labeled student. That is for Matlab. Click the download button there, squared in red, and it'll bring you to this page. You click the big blue button there in the middle of the page, it'll go to your downloads, and then you open up your no, you have to choose the installer first. So for me, I have a Mac, I chose the Mac OS, then it goes to your downloads, and then once it goes to your downloads, you open up the zip file, and it will automatically download to your computer from that point. Once you log in as the user that you use for MathWorks. And just to note, if you do have a Mac, you gotta have the OX software or the 10.9 software. So I think that my computer is too outdated for this. I can download the OX software and then get it, but I don't have the OX right now. It's free. And the 10.9 is not available for my computer, I don't believe. So in order for me to get Matlab, I need to download OX. And that's it. Pretty simple.
Okay, let's thank Dane. Any questions?
Were the people easy to get a hold of?
Yeah, I emailed them yesterday at like 7, so it was after business hours, and they got back to me this morning at 8:05 a.m. So that was, yeah, right away. And then when they sent me that agreement to sign, I signed it, printed it, sent it back to them by like 8:30, and then I think at like 8:45 they emailed me. So very quick.
You had better luck than I did. It took me like 3 days.
Oh, really? Yeah, otherwise Gregory Cook is normally very quick on responding too, so that's it.
More questions? If no, let's thank Dane once again. So right now we critically need appearance of John. So I will distribute his slides and give an introduction what he's going to present. But if he will not pop up, I don't know. I probably just show his slides myself.
couch.
To the couch.
Ah. I was going to replace you, but it's so much better if you do present. From yes, are you going to share content so that you scroll slides as you need?
Can you see them on your screen?
Yep.
Okay. Okay, so one of the first steps when we're done running coupling calculations on the HPC or one of our other systems is to take those coupling files and convert them into the Redfield tensor. And so this is important because it's going to allow us to have the data both in matrix form and a visual representation of transition probabilities for the sets of states that we're interested in. So, well, I guess
John, just a second. Please stop the audience and ask if anyone wants to. Otherwise, if anyone wants to stop you and ask you a question, because if you miss fundamentals, then there is no reason to go further. You better
Okay.
ask and lead the discussion.
Okay. Does anyone have a question at this point so far?
What is a coupling? Is it like a car part?
Very good question. Okay, so when we're interested in the dynamics of a system like Dr. Killen was talking about, we're interested in how electron density and the total wave function can change from one point in time to another with the motion of atomic positions. And so when we're able to calculate a total wave function for a set of atomic positions and do that, say, 1,000 times along a 1 picosecond trajectory, we're able to compare the wave function from one point in time to another. And so looking at this wave function overlap from one time to another is considered a non-abatic coupling.
Satisfied?
It's not a car part.
It was kind of
Not a car part.
made up because Aaron knew about it, but Daniel, Dane, and Fatima, do not hesitate. You may because in front of the rest of the world you will be leaders in this area. Ask now. So the couplings is the last thing that we covered on previous knowledge transfer session. So it is the, in some sort, probability for one electronic orbital to convert into another electronic orbital due to nuclear motion. But those coupling files are very raw material. You cannot immediately use them for computation. So you need to cook them to make them tasty. It is what John is doing.
How accurate are these probabilities, and are they believed to be true?
So we can get close to experimental values for certain types of systems. And so with our types of calculations, as with the majority of computational chemistry, there are approximations within our methodology that will fail for this type of system. And so the accuracy can be greatly reduced depending on the chemical system. But for materials that are more rigid, so pure inorganic materials, things that are confined, such as quantum dots that can be restricted to a single K point, our methods have been found to be reasonably accurate, at least up to this point.
I have a question.
Mm-hmm.
What is your title? Tell us from NAC to RRR. What is RRR? Or
Well,
you're going
so I guess-
to define it later?
Well, RRR is the symbol that we put in. It stands for the Redfield tensor. So anytime you see RRR inside the codes, that's what it's describing or trying to define parts of. And so the image on the right part of the screen there is a visualization of the tensor that is RRR, which will come out of the adiabatic couplings.
Okay. So in very rough saying, not for the general public, element of RRR of Redfield tensor is coupling element squared. So coupling is a matrix element of the non-diagonal matrix element of Hamiltonian, and RRR is a Fermi golden rule element, so matrix element squared. But do not tell it in public. There are much more details here. It's oversimplified, just to give general direction. Okay, please keep going.
Okay. So when we're interested in calculating this type of tensor, what we'll want to do is, on a local computer that has Matlab installed, build a new directory for Matlab. And in this directory, there's only 3 types of files that you need. The first one is the set of files that's produced during the coupling calculation. And so generally, they're just the coupling dot and then numerical value for some range that we were interested in. If we're looking at spin polarized calculations, you're going to see something come out as either coupling 0.01 and then numeric value and 0.02, or sometimes you might see up or down just depending on what was output within the script. So generally we have anywhere from 10 to 1,000 coupling files that we'll use for this calculation. The second type of file is the energy pop. And so an example of this energy pop file is on the right side of the screen. Basically what it is it's just a file that contains the list of electronic states generated within an electronic structure calculation. So on the screen itself, that was a screenshot from Matlab. So ignore the very left column because that's just a line number. So the last 3 columns in that image are just the orbital value, the energy of that orbital, and then the population. And so here we're able to see that in this case, we would find our HOMO value to be at 675, and then LUMO jumping up to the next one at 676. And so the third type of file that we'll need for this is labeled as a correlation file. And so there's going to be lots of iterations. So you might have a correlation underscore, version 2, or correlation underscore some other set of indicators that the person was using. But so this .m is a Matlab script type file. And so that's what we're going to need to take this energy pop and the coupling files and turn it into the Redfield tensor. And so there's a couple modifications that we'll need to make. One of the things is, so in the energy pop file, because we're reading all these files in as different matrices, what we'll want to do is we'll want to trim the energy pop file to include only the range of orbitals that was investigated during the coupling calculation. So if you look at the input overlap file in one of the directories from coupling, you should see 2 values, and those will be your initial and final states within this correlation file. And so I've highlighted the top chunk of the correlation file, and you can see it on the right. And so there's 4 things that we'll need to modify specific to our systems, listed on the bottom left and then color coordinated with the image on the right. So the top one is going to be an indication of what the HOMO value, what the orbital number is. And then the O min and O max are just the orbital minimum and orbital maximum in terms of just the index value given. So here, 630 to 700 is the range. And then the third thing we'll want to take a look at are the number of coupling files. So sometimes we're only interested in a very short period, so range from 1 to 10. Sometimes it's 1 to 1,000. And so inside the correlation file, you'll see there are loops. that build or read in all of the different numeric values for the coupling files. And so in this case, 2 of them are open because I shortened this up just to do some test runs. And then one of them I have commented out. But there's generally 3 different locations to just make sure that you can change it to where that value needs to be. The last thing is the number of steps to take. So in this example that I have on there, I only ran 1 through 10. And so you can see this line of TTT equals 10 minus 1. So that first value of 10 should equal whatever the highest coupling value is. And then the line below it is a time from 1 to 9. And so this 9 value is generally going to be the highest coupling value minus 2, or sorry, minus 1 there. And then again, you can see 10 is put back into that third line. So there are just 3 locations for when you're changing time you need to be aware of. And so execution of this is just like a standard Matlab script. You're going to be in your directory in Matlab, and you can either do it 2 ways. One is just to type in the name of the Matlab script and hit enter. Or if you double click that file and open it, there are options at the top to run the file. So you can do it either way. And if for some reason, you missed a number or things aren't equal with the indice values, you're going to see an error code pop up. And so the main results out of this are an RRR file, which is just a large matrix with the transition probability values that we'll use forward and going with producing the dynamics. But there's also some other things that get produced. So the RRR file itself, there's a .pdf that is an image, but there will also be a number of things that can pop up on your screen. So this .fig is just the Matlab figure file, and that you can go ahead and modify. And then there's also 2 plots of gap law. So their rates just versus the dissipated energy of the transition, and then a log value of this. And so there's 2 examples here. So the one on the left is just the rate versus the specific energy of that transition. And then the image on the right is the log of these rates versus the transition between 2 specified orbitals. And then best fit lines have been drawn in, at least with the script that I have. And so the main result visually is here in this RRR file. And so it should look something like this, where it's a bar plot, and you can see the majority of the values or large values are along the diagonal, which is what we would expect. Because those are going to be the transitions closest in energy. And so there's a script on the right that I use to try and automatically generate this. And so the rest of the files, or the rest of these slides, are just imaging things. So if you just would do a figure and then plot in your RRR, you'd see something like this. You can start putting in labels and markers, and do some changing to how it's visualized, just depending on your preferences, and coloration for something that looks a little bit better. And so this last slide, I don't know if it's in the version you have, but if you run the script and have this pasted in there, it should do everything for you, and this should be what pops up in your .fig image, and then you can just go in and export it as a PNG or TIFF or something. And so yeah, that is what I have.
Okay, well, thanks, John. So any questions? So if you're seeing it for the first time and never practiced, better ask now. Because John is going to defend thesis. He can be hired in far away from here, so use your chance to ask. Do not hesitate. You're not getting grades for questions.
So what do the RRR figures actually mean, really?
So what the RRR what this tensor provides is transition probability from one state to another. And so if you look on the X and Y axis on this plot, you'll see that there's things like LUMO plus 5, HOMO, and HOMO minus 5. And so if we're interested in a transition from, say, HOMO to LUMO, that would correspond to almost the very middle, I mean, not exactly the middle, but almost the very middle square that's on this plot. And so the amplitude or height of these bars is going to give us an idea of how likely this transition is. So say down here on the bottom, you have something that's, LUMO plus 10 to LUMO plus 11. There are these two tall red bars. So for that specific transition, the probability is high. But if you would go LUMO plus 10 to LUMO plus 9, there's almost no amplitude, meaning that transition is not likely to happen.
Make sense? More questions? If it is not the case, let's thank John once again. Oh, that's a nice image.
Whoops, that wasn't supposed to happen.
If you will wave the hand, you will see the delay. Or if you just turn the head, see?
Oh yeah.
So the next is Yun. So we will summarize what John has reported in the form of making sure that we are ready for the next step for doing actual dynamics, because John has explained how to convert the outcome of initial calculations. You need to push the share content button on this little okay, yeah. So couplings files come as an outcome of VASP calculations, standard computational chemistry software. Everyone after Yun will show how to run actual electrodynamics. John has presented how to convert the outcome of the VASP into the form that can be fed into the next step Matlab calculation. And Yun will help us to take care that the information, so to say, generated by John is very well prepared and ready for the next step, so that we have flawless funneling from one step to another.
Okay, so for the actual calculations of non-adiabatic dynamics, we need actually 5 input files. And the first one is the triple R, and this is the output from the Matlab code John has already talked about. And the next we need the energy pub file. And actually this one is obtained from geometry optimization calculations. And this is the same file which we use for the generation of absorption spectrum. And also we need for master EQ file. Actually, this is just oscillator strength in the matrix form, in the matrix format. And the next one is a band out. So this is just an integration of partial charge files. So basically, my understanding is this file. So when we do partial charge distribution, we can project this information into z-axis. And then we install this kind of information into band-out file. And then the final one is another Matlab code for charge carrier dynamics and also for photoluminescence. Okay, so this is how to get the full master EQ file. So basically, we go to the directory where we do geometry optimization calculations, and then we need to type this command just to create the input overlap file and to specify the orbital interval. Next, we can run this code, and after that, we can get the full master EQ. So this picture here show how this file look like, and then we can just rename it or copy full master EQ to full master optics. Here is the procedure to get the bandout file. So basically, we can create a new folder, and then we copy paste everything from geometry optimization to this new folder. And then we copy count car to postcar, and we also need additional in-car. And in this in-car file, we need to modify two things. The first one is number of bands. The next thing is the energy interval. So we need to make sure we can match with energy path file. In the following, we can just run WASP. So after the calculation is done, we can use this command. And basically, we just need to change one line. We need to change line number 6. So here, this one is the starting orbital, and the second one is the ending orbital. So finally, just run PERL to run this code.
Sorry, so when you go into band integrate.pl file, line 6 already looks like that, and you're just modifying the numbers that you want?
Yes, basically you just need to modify its number.
Just the
number.
Just that one number? Or both of them 1 and 61?
Both of them.
Okay.
The first one is 1, the second one is 61.
Would you ever modify those 2 pluses, or is that?
No.
Okay.
So after you type this PERL command, so everything goes fine, you'll see something like that. Okay, so now I guess we have all the necessary files. So we can just transfer these 5 files to a new folder at the local PC. And next, we can just run Matlab code for the charge carrier dynamics and the photoluminescence. That's it.
Okay, well, thank you, Ivan. So, are there questions? I have one. So, the band out file is needed for charge transfer. But if we are exploring systems that predominantly do not show any charge transfer, like luminescent material where charge stays at the same place and band out will not help anything. And we do not have time. For example, tomorrow we depart to the conference. Is there a way to avoid calculation of band out file, but keep all the codes intact?
Any suggestion?
If we know the number of orbitals in the energy pop, and we know the number of grid points along the line, we can just put blank matrix filled with zeros or any garbage, but of the right dimension, and then the code will eat it and just calculate something irrelevant for the charge transfer. But if you do not need it, then the code will be running and there will be no error messages.
I see.
More questions to Yuan? Daniel, Fatima, Jane?
Wait, so if you had no charge transfer, what would be the purpose of pulling up that graph? Because this information is to get to the point that John just presented on, right? This is prior to this is pre-John's presentation?
No, it is after John.
Oh, so you take John's, okay,
Okay?
okay.
Makes sense?
Yeah.
And if your question was, do we have, what are the situations when we do not need charge transfer? Or it is clear?
Well, I'm just, I guess, curious if, because if there was no charge transfer, wouldn't that graph, the RRR figure, wouldn't there just be like all flat? There would be no peaks?
I guess maybe this question is, so if we have a blank band out, we can still have the right green figure. For
Correct, correct.
Oh, this is for the green figure.
Yeah,
Okay.
it is still
okay.
correct.
So there are three processes. Well, right now I'm talking not as a scientist, but as a unskilled programmer. There are three things that we program there. First, occupation number for each orbital. How does it change with time? First. Second, how the average energy of electron change in time. And three, how the average position of electron in space change in time. So the main thing is only number one, is actual science. And number two and number three are just visualizations for specific applications. And there is number four that we will not cover this meeting, the emission spectrum. There are modifications of code that do it very efficiently. We just skip it for the sake of time. But we may arrange another knowledge transfer session maybe next semester on this.
Sorry, I guess just for my own clarification.
Yes,
So
yes, please.
what, like applicably, how beneficial is it to know the position of an electron if there's no charge transfer?
It is not beneficial. Therefore, we can not concentrate of the content of the band out file.
Okay.
I think.
Like
Well,
why?
when he says charge transfer, he means like between a donor and acceptor. Not like when you say charge transfer, do you think like charge between orbitals?
Yes.
No.
So in this context,
Just
it's
transfer in
between
space.
like molecules.
Okay, okay.
If your model, thank you, Aaron.
Yeah,
If the model doesn't have donor and acceptor, if it's just one molecule and charge stays on it, each orbital is equally delocalized, then even if you compute absorbers related to charge transfer, they will have just homogeneous trivial transfer.
Right, okay. Okay, thanks.
Okay, more questions to you?
I have a question.
Please.
Like in this band out slide, so this number, is it always like one? Is it one?
That depends on your system. So
So this number should be changed for different calculations?
So normally you need to make sure the numbers are in agreement with the energy path file for the generation of absorption spectrum.
Where do you get those numbers from? I'm sorry, I know you mentioned it, but like how would you choose 1 and 61? Just, I know they're different for each system, but where?
So, yeah, basically, so right now this is from my case. So for my system, I only have 60 orbitals, so I put 1 and 60. If you have large system, maybe
You consider all orbitals?
Yeah.
Okay.
Like, do you remember, or you dealt with the input overlap file before? It would be the same numbers from that file.
Okay.
Okay, let's thank you once again. next time we can share, or in the future we can share the, I don't know, is it a duty or pleasure to operate this little remote? Okay, so after everything has been prepared, we need to actually propagate the electron dynamics forward in time. So the practical details will be covered by Aaron in next talk after me, and I will give an overview of the actual Matlab script that does it, and give overview of a couple of equations that are being encoded in this script. So the code reads input data, input files as described by Yun. So list of energies and occupations in energy pop, the distributions, charge distributions for each orbital in band out, the most important part, the non-adiabatic couplings squared, the rates of the transfer between orbitals stored in the file RRR, and for master equation is the optical data, which are not needed at this step. I will not cover the luminescence. So since we are not trying to sell this code, it has never been polished to like click the button, everything will happen. So one needs to change a couple of numbers, not in the input data, but right in the body of the code, which is a not elegant style of programming, but maybe next generation of group members, if any, will fix it. So most important thing that all of us will modify as we deal with the code is this IH and IE, which stands for encoding of initial excitation. Just not want to speak too long. If you are exposed to TDDFT, right? You are. You know that actual excited state is the superposition of multiple electron hole pairs. They're correlated, there is an electron hole attraction, therefore energy of excitation is different than like HOMO-LUMO gap. But if the system is big, TDDFT is not possible. So here we are under approximation that excited state is just elementary HOMO-LUMO pair, not HOMO-LUMO. One occupied orbital and one unoccupied. There is no difficulty to expand further. Right now we are just doing elementary things. So in order to specify initial excitation, we tell how many orbitals below the HOMO where we take the electron, and how many electrons above the LUMO where we place the electron. Electron hole excitation. Then, and here, same as in the thing that John was doing, the leftmost part is the line of the code. So if the code has been distributed in the email, you can glance through and find just line and identify the right place. There are a couple of dozen of versions of the code, but I was checking that these correspond 10 minutes before the meeting. So then this loading of the energy pop file, and you see that energy pop has 3 columns. So the first column goes into this file, second column is energies goes to this file, and the last column is occupations go to this file. So again, we are going to follow the dynamics of electron that has been excited to the orbital IE, index of electron, and hole that been excited to IH, index of hole. So here we just load this red field indices. And here are some comments on the units in case you want to quote specific element of this 100 by 100 matrix for one of your debates with reviewer. And then you need to specify manually. It's possible to do by programming that code is parsing, but it's a little safer to do it manually. You specify where is highest occupied, where the orbital where your red field starts and orbital where your red field ends. Why? Why cannot we cover each to each orbital? Because if we do not do X-ray or UV spectroscopy, we will excite very few orbitals, or few tens or few hundreds orbitals near Homo Luma. If the system is big, we never will touch something that below 1000 or above 3000. So we need maybe 100 or 200 orbitals in the vicinity of the gap. And it saves tremendous amount of numerical effort. So the RRR file, even if the system does have 10,000 of orbitals, we can make RRR matrix 100 by 100 by having 50 above and 50 below. And this example is made for Aaron's system with so many orbitals. It is and it is in spin orbit stuff. So another approximation that we do neglect attraction of electron and hole. In eyes of some theorists, it is a big sin. But we are doing it because we want to cover truly large systems. There are approaches that can be immediately inserted into the code that will fix this problem, but then it will be too large to start with. So right now, the RRR file includes rates of thermally activated transitions between each to each orbitals, including both occupied and unoccupied. So there are 4 quadrants. If here we have rows and columns from 0, it is not actually 0, it is from 50 below Homo. The middle is about Homo, and 100 is about 50 above Homo. So the lower quadrant here in blue corresponds to holes, and inside the quadrant it's rates of transitions from hole to hole. The upper quadrant here, the yellow, it is a rates of transition from unoccupied to unoccupied for electrons. And those off-diagonal quadrants would correspond to non-radiative transitions from occupied to unoccupied. It's a probability that an electron from occupied orbital will jump up to unoccupied because of thermal motion of nuclei. See, it is 0, or very close to 0. And in the middle, there are probabilities that such transition will happen on the Homo Luma, which will correspond to non-radiative recombination. It is small but not 0, and sometimes we quote it. John did quote it in his paper on lifetime of excitations in perovskite quantum dots. And we all can do it. It's just picking one number from this matrix, and it's already a very valuable thing right in the middle. But we propagate electrons separately from holes. And you see here are zeros, so we can cancel these 2 quadrants and play only for rates for holes and rates for electrons. So if we look from the middle, from the upper quadrant, which is encoded in this long line, then we will look only on this part of the RRR file, focusing only on electrons. One thing. Another, right now, RRR file has equal probabilities for going up and down in energy, like from HOMO to HOMO from here, from LUMO to LUMO plus 1, and from LUMO to LUMO, from LUMO plus 1 to LUMO will be the same rate. But by the principle of, Fatima, did you took statistical mechanics? So when you have different probabilities going up and down, how do you call it? Detailed balance, right? By principle of detailed balance, this probability is different. It should match the Boltzmann distribution, and here we do another approximation. We can't do exact following of the detailed balance and make the transitions up and down higher or lower depending on the temperature. Here we make another strong approximation. We just cancel the rates of transition that do lead to increase of energy. So we keep only those transitions that decrease the total energy. Therefore, we parse this quadrant. So this is only for electrons. You see, it's 50 by 50, and 1/2 of this quadrant is multiplied by 0. So this is encoded in these lines, and it is approximate way to match detailed balance. Those who will work further on the code would need to make it temperature dependent and allow transitions up in energy. And even there are some parts of the code that do it, you just cancel it to make it simple and clear. So right now, we are looking only on electrons. For the holes will be the same story. So electrons, one particle, one electron that has been promoted to the originally empty orbitals. And for each orbital in the conduction band, from each to each, we have this former RRR file, which is now called RE, like red field for electrons. Questions? Okay. So a little technical details. I'm not blocking. So here is the problem that John was facing and resolving. If your couplings have been computed at different temperatures, if your system does have subgaps, if the energy offset between orbitals is large enough, the rate of transitions can be very, very small. So it can range by several orders of magnitude. Aaron also, we all were facing it, or we will face it. Aaron did have the 3 orders of magnitude difference because the transfer was through bond or through space. And you did see this effect by having materials with very large gap. So we need to be able to cover like from femtoseconds to seconds, or at least to microseconds, or right? So if we will have it, we need to propagate forward in time. But if you will make time step smaller than femtosecond, it's good, but it is too expensive. If you have time step larger than femtosecond, we can, but if you take like 1, 2, 3, and if you go to nanosecond, to picosecond, it will be 1,000 steps. If you want to go to nanosecond, it will be how many? Million steps. If you want to go to whatever is next, milliseconds or microseconds? Microseconds. Then we need to do billion steps, which can throw the head of our computer. Therefore, we are doing non-equal time step. Each step has different lengths. And later you will see that it is allowed here. So the time step expands exponentially. So through this equation, we have a grid which is spaced equally, about 500 time steps, but offset between actual value of time spaces non-evenly. When we look on a short time, they're spaced very finely close to each other. When we are looking to longer and longer distances, the offset increases. So it is encoded in here. The variable S will be needed later when we will do green figures for energy distribution, and therefore it has the size of the grid, which is spans all energies where orbitals of our interest are inserted with fine enough step. Okay, so remember our discussion with Dane. First programming step, second programming step, third. Occupation of orbitals, distribution in energy, distribution in space. Energy and space are just visual, but occupation of orbitals is main thing that this code is doing. So in few slides, right now I'm showing it a little too early, but otherwise we will be bored. So it is the goal that we will reach in 3 slides. So it is occupation of each orbital in the conduction band if the no, it doesn't allow annotation right now. If originally we put 100% occupation to LUMO plus 10, right? So as time passes by, it will lose occupation, and some orbitals, LUMO plus 9, plus 8, plus 7, will gain a little occupation. The LUMO itself was empty, and as time passes by, it will gain all population. So it will be cascade thermalization that we are modeling. These time steps, right now they are discrete, but in fact, between they are non-equally spaced. At the very beginning, the spacing is about femtosecond. At the very end, the spacing is more than a picosecond. It's just increasing step. So the trick, numerical trick to do this code was borrowed from very elementary approach to basic quantum mechanics, where main principle that one takes Hamiltonian, diagonalizes, gets eigenvectors, and use them, and each of them evolves in time with right frequency. This idea of the quantum mechanics, where one diagonalizes Hamiltonian, can be extrapolated to a very different type of operators and very different type of eigenvectors. So right now we will use the same coding style, but we will think about completely different things. So we will diagonalize not Hamiltonian, but operator of Liouville plus Redfield. So Liouvillean operator diagonalization, Redfield operator diagonalization. Eigenvectors will be not the eigenstate of Hamiltonian. It will be something that is hard to imagine. So right now it's mathematical abstraction. So, but the core calculation was borrowed from there, and some notations a little non-ideal. So psi here it is the same name as one would use for wave function, but it is not wave function. So it is initial state for occupation of electron orbitals. I'm not showing it here, but this time step number 1, here all range of orbitals, and it was set up that all of them are equal to 0 except the one that corresponds to index of electron, IE. So we do set it up. Now we set up the size of our space. It is last orbital included in the RRR minus HOMA, so only upper quadrant. And the matrix RE is our quadrant that corresponds whatever comes from red field related only to L vectors. So if you would do this coding in C++ or in Fortran, this line would expand in 20 lines or maybe 200 lines, or just calling some linear algebra packages with subroutines. But in Matlab, it is just one line of diagonalizing matrix RE and funneling the results of diagonalization into objects. So eigenvalues coming into the second one, into the D, and eigenvectors are stored in matrix form, 1, 2nd, 3rd, and stored in this matrix U. So this is numerical solution of eigenvalue problem. I have a big temptation to say that the rest is trivial. So Liouvillean plus Redfield act on density matrix eigenvector. Density matrix eigenvector gives this eigen frequency and again eigenvector. After we get these eigenvalues and eigenvectors, we need to match initial conditions. So this solution will be universal for any initial conditions. In fact, we know we have potential to know everything after we do this diagonalization, but it doesn't help us, this knowledge. We need to get something that we can observe for specific initial excitation. So we need to match initial condition. Therefore, this is another excellent thing in Matlab. It is solution of system of linear differential equations, like this 100 equations in one line. So we find expansion coefficients. We find this vector C will tell projection of the initial state onto each of eigenvectors. So this vector C, which will have the same size as many orbitals in conduction band, will tell how much given eigenvector contributes to this initial condition. And we solve for this initial condition at time 0. Again, how much given eigenvector contributes to given initial condition. Now we construct time propagation. So we take the eigenvector of density matrix of Liouville Redfield operator that we found through diagonalization. It evolves in time as exponential to the power of this eigen frequency times time. And right now it is not things that in quantum mechanics, but it is standard thing in linear differential equation, right? And here this, it's not the best notation, I just didn't found something better. It is the thing that we stored in the vector C, initial conditions, projections of the density matrix at initial time, at time 0, onto each of eigenvectors. So each eigenvector contributes to solution with such proportion which depends on initial condition, right? And then we make summation, this letter, strange letter of Xi just runs over all eigenvectors.
So it's a ket or a Bra and a ket.
Let's not do Bra and ket because it is we will in space. We will make it. It's not the best notation.
So this one is just the C input.
Yes, from one angular bracket to another one, it is a letter C. So this row for indices I and j bigger than homo are found in these lines. So this vec is parsing the eigen expansion coefficient number k out, so it is a mask that by it will be 1 at the place corresponding k and zeros before and after. So if you multiply this mask by vector c, then we will get contribution only for one value of this index. So we add together all summation that we did before plus expansion coefficient. Sorry, this vector is used to parse eigenvector. This is by index. So by multiplying matrix of all eigenvectors by this vec object, we will get only one eigenvector. And then the time evolution is gotten by frequency number k times t. Okay, and then we add all of them together and get the dynamics of only diagonal elements of density matrix for the electrons. If we expand this code further, and we need to include off-diagonal elements as well, but there is a theorem that in several cases one can propagate them separately. And I do have versions of the code with off-diagonals, but again, it's all grows to a size that we cannot review in one meeting. Any questions to here? So it matches your favorite subject of linear differential equations that you recently took.
I didn't like any of them.
Huh?
I didn't like any of that class.
Okay. And this line is not needed. If everything is encoded correctly, change nothing. I just did it as a safety emergency just in case. If you do numerical propagation, sometimes the norm is not conserved, and this is just normalizes this occupation so that their summation always is equal to 1. But it's just a numerical measure. Adds nothing to the algorithm. And here we are funneling. So this psi, actually it is the diagonal part of density matrix for electrons as function of time. But the name psi is not ideal for such object, so we put it into PPE. I didn't find better name because I do not know the letter rho on the keyboard. P just because my hand was shaking, and E for electron. For holes it will be PPH. So I'm skipping the things for PPH, otherwise we will be out of time. So then remember, occupation of electrons, distribution in energy, distribution in space. We are done with occupation of orbitals. It was in this place before. Now we are looking onto distribution in energy. So again, I'm showing the outcome before, otherwise it will be too boring to follow. So this is the main outcome of the code. If you learn how to generate it, you can do competitive publications. You need to invest time into being able to generate them for different initial conditions, for atomistically computed couplings. So what does it mean? This corresponds to excitation at time 0. We take an electron from occupied orbital and promote it to unoccupied. So the blue corresponds to absence of electron, yellow corresponds to presence of electron, and green means the distribution is the same as for ground state. And as time passes by, the electron dissipates its energy into thermal vibrations. So its energy drops from LUMO plus 10 to LUMO. Hole also dissipates energy into thermal vibration, and therefore it floats up to the maximum of the valence band. So after some time they end up on the HOMO and LUMO, on the edges of the bands. Okay? So how do we program it? We take the occupation of each orbital at each time and multiply it by distribution function that is centered at the energy of given orbital. Right? And under this delta, we understand not true delta function, but something with finite width. So, and then we subtract the equilibrium distribution for green. Slice. So it is distribution at time t is PPE, which is element of density matrix of orbital I at time t, times exponential of Gaussian, with Gaussian representing this delta function at energy of electron orbital number I, right? Since those are continuous functions, then instead of sharp peak only in the exactly energy of orbitals, we get kind of smearing. And this is especially important if you have very high density, or if the energies of orbitals change in time. And then the slice for each time step is accumulated into matrix that is growing bigger and bigger at each time step, and then it accumulates so that on one dimension it will be energy, about 500 steps for different values of energy, and on another axis it will be time steps. So this S, at this point, it will be upper part of this image. Make sense? Okay. Yeah, we can plot it. Here you see since time steps are non-equal, we can either request logarithmic plot or we can do linear plot, but on the x-axis show log of time, so that we cover from picosecond to the -3, which is femtosecond, 10 femtoseconds, 100 femtoseconds, 1 picosecond, 10 picosecond, 100 picoseconds, 1 nanosecond. So here we are plotting, maybe I just by error deleted the slide, but these lines, dashed and non-dashed, corresponds to average energy of electron and average energy of hole. Let's see. Yes. So we take energy of orbital times occupation of orbital and run over all orbitals. And then this is weighting. Weighting, not like I'm waiting for the bus. Weighting like giving weight to probability. It's probability that this energy was found, right? And then if sum of all probabilities is 1, then after the summation, it will be expectation value of energy. So this dashed line is this expectation value of energy as function of time, which is PPE times energy, which is stored in a vector. We are very close to beginning of Aaron's presentation and end of May. So another approximation, if we assume that this function is a linear decrease, then we can extract approximate time when it experiences this transfer from excited to non-excited. So something a little bit shorter, or of the order of 1 picosecond, by this expression. If you hate this expression or do not like it, you can just numerically take this line, feed it into Excel, and make fitting to single exponential or something else, or to the origin. But I'm doing it very simple way, almost manually, simple programming. So this equation corresponds to fitting to a single exponential decay. And then for electron, it gets the rate of 2 point something inverse picoseconds. If the rate is 2 inverse picoseconds, or 2 picoseconds minus first, it means that time of transfer will be 1 divided by this number, which will be half of a picosecond, right? Make sense? So it's 1 picosecond, and it experiences this transition somewhere before 0. So it agrees with this figure, but it gives more algorithmic way how these numbers were obtained. The whole relaxes later, therefore the rate is lower, right? So these two numbers can pop up in the command line of Matlab after each run of the code. One of the standard tasks that we do, compute everything, as Yulun has explained and everyone before me, and then play with the two very first lines that I declared at the first 10 seconds of my presentation. Index electron, IE, and index of hole, IH. Change initial excitation and see how the rates respond to the change of initial excitation. This is a very simple thing to do practically, but it is something valuable and unique that standard codes do not have, and that we can attract attention of experimentalists who are doing time-resolved experiments like femtosecond spectroscopy or whatever. Response of the relaxation rates to initial excitation.
How does the code know that the first relaxation isn't the one that it should report out?
Right now, this version of the code assumes that everything goes as a single exponential, which is here it is a lie. It is 1 exponential then second. I'm not telling that this one is the best, and you are exploring this opportunity and splitting the time range on 2 intervals. Mm-hmm. But these things can be included if you make it a commercial code for sale, like a Gaussian for 10,000 license, or we can do individually in our research projects. But if you want to have something simple that we can explain in 20 minutes or whatever, a couple of hours, then let's start with simple things. It's not ideal. It is a very strong approximation. Another parameter is what we take as an infinity in this equation. Well, infinity is the last point of simulation, whatever, nanosecond or how much time we have we span over. There is a unit of code to do the third thing, the distribution of charge in space for charge transfer, and there is a fourth thing that is in the descendant code for photoluminescence. No time right now. This could be the last slide. Yes. Any questions? Any questions? 1? Any questions? 2? Any questions? 3. Okay, I'm free. And the next presentation is by Aaron, who will teach us more on practical aspects of running this code. Right now this camera is tuned to there, but if you do not like walking there, I can focus it on you. And oh, here, so I can distribute.
Yeah, so as Dimitri mentioned, this is more just a primer on the practical things you have to know on how to actually just run the software based on the things you want to simulate. So when you open the code, the first thing you're going to see is this top line here, IH and IE, and those basically just change your initial conditions for the optical transitions you want to look at. So in principle, you can choose any numbers that you put in there. The code would probably run it, but you want to choose good ones so reviewers don't ask you like, why are you looking at these transitions? So normally we want these to correspond to your oscillator strengths, which you compute earlier. So you would already know those values. You would just have to look them up in the cluster before you run the simulation. And so on the right-hand side, it kind of shows you what each of these parameters respond to. So for IH equals 1, that would correspond to your HOMO, and then IE equals 1 would be your LUMO. So yeah, it's just good to have those in mind when you're going through all these, knowing which parameter corresponds to which orbital. Because I don't know, when I first did this, I always got confused because I always thought my HOMO, or I was confused like my LUMO plus 6 with some indice for some orbital I was looking at. So it's easy to confuse yourself, so you want to have this down. So that's how we create our initial conditions. So to get our relaxation rates, it's actually pretty easy. We just you have this run button on the top. Once you put in all the parameters that you need to change, you just click run, and I'll probably sit there for 30 seconds trying to crank out all the computations that Dimitri just went over, and then it was all like there'll be a bunch of things that show up in the command window, but at the very end you'll get your KE and your KH, which correspond to your relaxation rates for your electron in your hole. And as Dimitri said earlier, those are in picoseconds, and they'll always be in picoseconds unless you change it in the code. And then along with the relaxation rates, you also have a couple of figures that will pop up after you click the run button. So one of them is on the top right, is the time evolution of your electron and hole in space. So so on the left is the image that shows up, and on the right is just a overlay of the HOMO and the LUMO orbital on a donor acceptor model that I was working on over the summer. And you kind of see how these changes in the colors correspond to changes in charge occupation on your model. So you can see right away that right at the excitation, the electron and the hole, they're kind of occupied on the top of this slab here. And after time, the hole is going to jump up onto this dye molecule, and then the electron is going to separate down to the bottom of the model I have. So that's kind of how you interpret these time evolution of the orbitals in time. And then the other one that will pop up is your time evolution of energy occupation states. And then normally they don't have all these extra added on features. Those I had for a presentation. But your initial excitation is your LUMO plus Y for your electron and your HOMO minus X for your hole. And those will evolve in time. And I kind of just marked out for visual presentations of when the relaxation occurs in these systems. And then so then the colored lines correspond to the energy expectation values for like each band in your material. So on the right, I just kind of made a little mini bands for your HOMO and LUMO. So right away, your expectation value would correspond to the energy level down here, and it just kind of relaxes up over time, or relaxes to the band edges. And yeah, that's all I had to show for my presentation.
Okay, let's thank Aaron. So any questions?
I'm not too familiar with what a electron hole distribution means. Can you go over that really quickly?
Sure. So by that I mean, it's kind of tricky. So I'm talking about distribution in space.
Yes.
So it's like your CompChem orbitals. It's like where your charges are in time. So like here we can see initially that the distribution are, well, I guess I use the word distributions because like your electron and hole they're not points, right? They're kind of clouds of charge. So that's what I mean by distribution. So it's just like your orbitals where they track over time
Oh,
in space, if that makes sense.
I don't know what happened. Did you got?
yeah.
Okay. Huh?
3.
You can play with it. So more questions to Aaron? If no, let's thank him once again. So
Kick them out.
I don't know what is going on, but many thanks for
You are the only
This-
participant in the conference.
inspiring presentation, set of inspiring presentations. Right now, I do not see if it has been recorded, but if not, at least during the meeting, you've got enough ideas. So please do not hesitate to ask each other authors of the talks or just discuss, because it is really valuable skills that from idealistic point of view will just help humankind and other scientists to understand more about nature, and from scenic point of view will secure acceptance of your publications and success in your careers. Okay, so next time I believe it will be John Drill for his thesis. So everyone can just relax. Well, so to say. And John, John will work. Did you saw my email about the Sunnybell?
I don't think I did.
I was trying to forward it. So it looks like they want to push deadline from last day of year to last day of November.
I think that was just for early registration.
And for awards.
It is for awards too.
They tell that if you were awarded in the past, that you are not eligible. So those of us who got the awards may not care. John did it last year, right?
Are
And-
ineligible? If you got an award, you're ineligible?
For the next year.
Oh.
Because they before, like 10 years ago, they were so rich, they were given large amount of much fatter awards. They were announcing it ahead of time, so it was possible to apply, wait if you get notification of award, and then if I'm getting an award, I will go. If not, I will stay home. This now they try to protect themselves from this step, and they tell that the award is assigned only at the last day of the conference, only to those who has physically participated and paid all registration fees. But if we want to be, many of us may want to be eligible for this travel, and it means that we need to compose abstracts and submit application materials a month earlier. And if you select me as recommendation writer, it means I need to compose this much recommendations before that. Okay, well, I do not have camera to tell that meeting is dismissed, but you can see it evidently. Aaron, did you get this code for
Matlab?
logpod?
Yeah, you sent me the links to the directory.
Yes, so there will be a couple of students who will need your help.
Okay.
If they will be not hesitant, they will just knock to your door. If they will be hesitant, I will be a middleman
Day after tomorrow.
to forward your data to them.
Are you available
But
the day after tomorrow?
I have
Thursday. I mean Thursday.
yes 1 to 2 students for logpod and 1 to 2 students for
Yeah, just
Marcus.
send an email before you.
which means equilibrium for different electronic configurations, and then
So it'd be just a bunch of fair week calculations, right?
yeah.
Yeah.
And since they are, yes, it is not recorded. Okay, then you've got a unique thing.
So I do have a question for you for Eric's class. So just for the presentation I have to do, I just want to create like a toy model for the spin over coupling. So one thing I thought I could do, so I need some sort of wave function that has, that has all those quantum numbers. So I know from the class, well initially like I thought the simplest model would just be to do particle in a box. I don't know.
Wait, those are 4 quantum numbers for 1 electron in like hydrogen. Principal,
You're
orbit,
right.
orbital,
Your call will be disconnected.
magnetic and spin, right? So there is no, it's only 1 electron.
Yes, but we did go over an example where it's like we do particle in a box that has angular momentum that we went over in class. So that's well,
Okay.
that would give me the L anyway. So then I figured to get my spins, like I would take my L wave function, multiply it by the what letter should I use? Alpha. By spinor orbitals. I don't know if that would be a good way to construct a model. So this would be particle in a box with angular momentum, and then multiply it to spin orbitals.
Yes. Yes.
That could be done.
Mm-hmm.
Okay. Then I could just do 1 particle in a box with no spin orbit, 1 particle in a box with spin orbit
Yes.
potential, and then see if it's actually solvable.
Yep.
Or hope it is anyway. Okay. Yeah, I guess I'll just have to sit down and see if I can get the technical parts. But at least I know in principle it can be done.
Is there time constraint?
It just has to be done by the first week of next month.
Okay.
First week of December.
Okay.
So I still have like 2
So
or 3 weeks.
there is no rush.
Right. I still have a couple of weeks to try to work on it.
Okay.
Yeah, okay. I'm just curious about your schedule. Are you very busy right now? Because I have another manuscript, so if you're busy, I'll keep working on it. Just keep
Keep working. It
Okay.
will be no reason to give me more manuscript before I process the previous ones.
Okay.
So it is on Celine?
Yeah.
Okay, yeah, I'm very interested, but just as a fair game, I need to do my homework on
Okay.
previous one.
Yeah, sounds great.
Will you have time to help undergrads for their projects?
Yes, I guess so.
Okay, so I've got a couple of students who need help in getting potential of reactions as like reaction coordinate, whatever we define, and then think as you did for monomethyl hydrazine. You can. They need such type of data. Right?
Just the potential value?
Hmm?
Just the potential value?
Yes, but like values of the interatomic distances